Most developers treat the internet as an abstraction. You write code, hit deploy, and it lives in a borderless, instantaneous void, detached from physical reality. But every digital request, no matter how elegant the code, is ultimately bottlenecked by heavy, vulnerable physical machinery. Beneath the software layer, the internet operates on massive data center server racks and millions of miles of deep-sea submarine cables. These cables encase fragile glass fibers in thick steel armor and copper tubing to survive the extreme pressures of the ocean floor. The appearance of a seamless global network depends on an intensely engineered physical reality. To understand how global connectivity actually functions, we have to strip away the concept of the cloud and examine the system starting from the physical layer upwards. This requires looking at the exact intersection of optical physics and software routing frameworks required to move data across massive geographic divides. Software routing remains subservient to the limits of physical infrastructure. We begin at the absolute baseline of networking, Layer 1. This is the interior of a single strand of optical fiber. Down here, data does not exist as binary code or electrical currents. It exists as highly modulated photons, fired by lasers through a microscopic core of silica glass. The light stays inside the fiber due to total internal reflection. When a light wave hits the boundary between the core and its outer cladding at a shallow angle, it bounces continuously. Containing these photons allows the fiber to transmit massive, high-speed data throughput. However, this transmission mechanism faces a strict physical constraint, geographic distance. As these photons travel through thousands of miles of transoceanic cable, the signal undergoes attenuation. Attenuation is the gradual loss of signal strength and clarity over distance. Even the purest silica glass contains microscopic impurities. Over long distances, these molecules inevitably absorb and scatter the traveling photons. This chart plots signal strength against distance in kilometers. It reveals a harsh mathematical reality. As the physical distance increases, the integrity of the optical signal drops exponentially. Without mechanical intervention, a data packet sent from New York becomes unreadable noise long before it reaches the shores of London. The engineering of the global internet is defined by fighting the literal decay of light across oceans. Zooming out from the microscopic fiber, we face the macroscopic reality of cables stretching across the ocean floor. To combat signal attenuation, engineers deploy hardware solutions known as optical amplifiers, or repeaters. These are massive, highly pressurized hardware modules spliced lumpectly into the submarine cables at regular intervals, usually every 50 to 100 kilometers. Inside the repeater, a secondary pump laser injects raw energy directly into the weakened optical signal, causing the exiting waveform's amplitude to instantly spike. This optical amplification preserves the original data pattern without the latency penalty of converting light back into electrical signals. After hopping through dozens of these repeaters, the amplified signal finally ascends from the deep ocean and arrives at a terrestrial landing station on the coast. The landing station marks the critical transition point where the optical journey terminates. Here, optical transceiver hardware physically catches the incoming photons. The transceivers use the precise timing of those light pulses to trigger electrical logic gates. This step successfully translates physical bursts of light back into the standard ones and zeros utilized by computer servers. These deep-sea amplifiers and coastal transceivers are the invisible mechanisms making transoceanic data appear instantaneous to the end user. Now that the data is electrical, we move up the stack, shifting from physical hardware constraints to logical software frameworks. The system faces the problem of pathfinding. An electrical data packet must determine exactly which physical cables it needs to traverse to reach its specific global destination. The essential software framework that dictates this movement is BGP, or Border Gateway Protocol. BGP is a mapping protocol connecting thousands of autonomous systems, massive networks unified by single routing policies. When a packet moves, BGP evaluates all routes based on network policies, physical distance, and connection health, selecting the most mathematically efficient path. Connections rely on vulnerable physical hardware. Cables are frequently severed by ship anchors or seismic activity. When a link breaks, BGP initiates a self-healing response, instantly recalculating the map to establish a completely new alternative route around the failure. This mathematical recalculation occurs in milliseconds. It happens so quickly that it remains entirely invisible to both the software engineer and the end user. Through this process, BGP takes the raw hazards of physical geography and hardware failure and abstracts them into a manageable system of mathematical logic. BGP is the critical software framework keeping the data moving, masking the inherent fragility of the underlying hardware. We can now step back and view this entire architecture of global connectivity operating as a single simultaneous stack. At the foundation, photons travel through submarine cables. Directly above sits the middle layer of physical hardware nodes, repeaters and coastal stations amplifying optical signals. Wrapping over it is the topological layer, BGP paths dynamically shifting data across the nodes below. Global communication requires continuous millisecond by millisecond synchronization across all three of these disparate layers. This immense mechanical and logical complexity happens every time a developer makes a single API request. The concept of a cloud dissolves when confronted with the mechanical requirements of global communication. The modern internet functions as the most geographically expansive, fragile, and complex physical machine ever engineered by humanity. Understanding this physical hardware reality and its precise intersection with software is the mandatory foundation for engineering the future of global connectivity.